Hello everyone, my name is Yang Chiu Song. I come from Hong Kong University of Science and Technology. I will introduce the third part of the tutorial, which is about healthcare related knowledge graph construction and inferences. I will first give a brief introduction to knowledge graphs and then introduce how we're going to construct a knowledge graph and then make inferences using related machine learning techniques. So first of all, what is a knowledge graph? A knowledge graph may have different names. For example, semantic networks, knowledge base, or ontology. The term knowledge graph was officially used by Google in 2012. It has been used to support many search queries such as entity fact-checking and question answering. Here is an example of a search result with the query Anthony Fauci. On the right-hand side, Google Knowledge Graph returns some key attributes of this entity. Here's another example. When you search COVID-19, Google Knowledge Graph returns the key facts that are almost real-time updated. So here is a comparison of current state-of-the-art enterprise-level knowledge graphs. For example, as of 2019, Google has 1 billion nodes and 70 billion edges in its knowledge graph. Other giant companies also have similar scales. As you can see, not only search engines, but also recommender systems and social networks, they all have their own knowledge graphs. Google Knowledge Graph is also used in healthcare. For example, it has been used to support diagnosis decisions or checking symptoms. Like in Google Health, which was released in 2015, they demonstrated that the aggregated search result can formulate a healthcare-related knowledge graph. The knowledge graph can then be used to support multifaceted search. The Google Health Knowledge Graph has been carefully checked and reviewed by medical doctors and thus considered to be accurate for many diseases. Here is another example of knowledge graph about symptoms and diseases. The knowledge graph is constructed based on the biomedical literature database PubMed. As you can see from a subgraph on the left, two similar diseases have similar symptoms, but different symptoms have different weights that co-occur with the diseases. For example, both diseases are related to diarrhea, which is the most typical symptom here. But Crohn's disease is more related to edema and acute abdomen. While ulcerative colitis is more related to headache and constipation. So on the right-hand side of the figure, the graph of disease shows that the similarity actually reveals some interesting patterns of clusters. So the disease symptom network can be further used to analyze different kinds of disease similarities. For example, on the left, we construct the disease similarity based on symptoms. And on the right, we construct a similarity based on PPI networks. So the similarity can be based on either shared genes or first-order, second-order interactions. Then we can compare the two similarity networks. It's shown that they are highly correlated, but there are still some differences. We may be able to mine such disease symptom relationships or to mine more PP interactions based on this. Another example is to extract the symptom and disease relations from large-scale electronic health record. Here is an example where the biomedical concepts are detected from EHR data and then linked to an existing knowledge base to have a unique concept ID. And where the concept can be either symptoms and diseases. Then the concept patient relation matrix can be built to construct the symptom disease relations using some statistical models. So here I show two figures of the same same two diseases. It's obvious that the relations detected from EHR are different from the ones extracted from PubMed literature. As EHR is more statistical, noisier than literature, some statistical models needed to be applied here. On the other hand, PubMed is more likely to be formal articles written by researchers, so they tend to only mention typical symptoms to promote learning. Here I show the precision recall graph of the extracted symptom disease relations examined by medical doctors to give you some sense about the results. The Google Health Knowledge Graph shows very high precision for both most typical symptoms as well as frequent symptoms. But the recall is lower than 40%, even for frequent ones. On the other hand, the automatically extracted relations shows very good recall, but the precision is not as good as human curated ones. So as you can see, information extraction and text mining plays a key role in knowledge graph construction for healthcare. However, natural language could be very ambiguous. For example, one disease may have different names. Or one name, such as obesity, can point to different diseases, diagnoses, phenomena, or symptoms. So there are many existing annotated knowledge bases. You need to link to the text. You need to link the text to existing knowledge bases to leverage all of them for the inference. So the scale of the knowledge base are usually very large and cover many subdomains. So you may wonder, there are already many existing knowledge bases annotated by experts. Why should I do information extraction and build knowledge graph again? The first reason is that there is a lot of new information published and collected by EHR and PubMed. Medical doctors are overwhelmed by such information. Second, we need an efficient tool to process the knowledge to reason over different types of concepts. Traditional tools such as logical inference may not be able to handle such large scale of heterogeneous sources and ambiguities. Moreover, there are many new kinds of knowledge corresponding even more than the representation of the first order logic, such as the activities, states, events, and their relations. Therefore, we need to investigate what we can do with information extraction here. So for example, for the current COVID-19 pandemic, it's not possible to find existing knowledge bases. Most of the knowledge is shared in the literature of the research articles. So automatically extract information would help organization of what we have known so far and help doctors develop their knowledge and the strategy to deal with the disease. Here I show some existing COVID-19 related knowledge graphs. The first one is led by UIUC, and they have extracted tens of thousands of nodes with hundreds of types. A distinctive feature of their knowledge graph is that they can access different modalities of data, such as figures in research papers. Another one was done by Berkeley Lab. They also extracted tens of thousands of entities emphasizing on more drugs and genes. UT Austin's knowledge graph also has hundreds of thousands nodes. An interesting result shown in their paper is that they retrieved the related disease and drugs to the new drug, remdesivir. There are also some industrial efforts, and they built their even larger knowledge graph. Currently, the knowledge graph is only available through a demo. Next, I will introduce how we're going to construct such kind of knowledge graph from text and what can be done in the future to improve it. In general, information extraction can be categorized in different tasks. For entities and events. For entities, we need to excuse me. For entities, we need to extract the entity mentions in text and then categorize them or linking them to existing knowledge bases. For events, we also extract them to build their relations. Information extraction from text can be pattern-based or learning-based. Pattern-based approach usually use designed rules to extract information that reflects humans' knowledge about language. When there's less annotated data, pattern-based approach can perform better. is especially good when considering OpenIE, where there is no predefined predicate or targeted relations in the knowledge base. On the other hand, when there is sufficient annotation, learning-based methods usually perform better as they have better generalization abilities to read more irregular text. Here I'm going to show you an example of patterns that can be used to extract useful knowledge. Some patterns are commonly used for general IE, but medical documents are usually written in written languages, and sometimes can be long sentences. So to improve recall, patterns may be extended. For example, in this sentence, in longs and in reds should be both aligned to previous subjects and predicate. Another issue is that after such pattern-based extraction, the predicates are not aligned. So usually a clustering-based method should be applied here to normalize the relations. Compared to pattern-based methods, learning-based methods are now becoming more popular. Especially nowadays, we have giant pre-trained models. This has also influenced biomedical data extraction. For example, in biomedical domain, many BERT-based language models have been trained, which are generally used to generate more like some good contextualized word embeddings for text. Then the learning models will be applied based on the embeddings for downstream tasks. Here is one of the state-of-the-art BERT-based model, BioBERT. It's shown that it's very effective in many tasks. In general, the standard BERT-based model is fine-tuned over some biomedical related articles, such as PubMed abstract and full articles. Then different tasks are fine-tuned based on different kinds of supervision signals, like name entity recognition or relation extraction and so on. Now we start to introduce different information extraction tasks. We start from mention detection and entity typing, since these two tasks are highly related. To detect the mentions, we treat it as a word token classification problem. A typical label encoding mechanism is to decide the mention boundary by the beginning and the inset part. Then all other tokens are considered as outside. For example, in this sentence, we only need to label B disease and I disease labels to detect the right mention of that type. There have been many loss functions developed for such sequential tagging problems, such as using conditional random field. The mechanism can also be easily reduced to purely working on mention detection, where we simply set the labels to be B, I, and O's. In this case, we may have more training examples for each label, but if we want to do typing later, we need to build another model to get the classes of the entity types. Sometimes entity linking can improve entity typing, especially for fine-grained entity typing. The task of entity typing is usually trained based on distant supervision, where the annotation are weak signals, which could be simply anchor links in Wikipedia. So in this case, besides the weak supervision, when an entity can be linked to Wikipedia page, the categories of that page can also help to decide which type of the entity should be classified. Here is an example of the labeled results. The typing task has 72 entity types, including common biomedical types, as well as some COVID-19 specific types, such as coronavirus and immune responses. The results have been included in the UIUC knowledge graph. Different from typing, which tries to decide the category of an entity, entity linking tries to link the mention to an existing knowledge base. Entity linking can also be done with a two-step approach, where mention detection can be firstly performed, and then we do entity disambiguation. So the loss of entity disaggregation is usually a ranking loss related to a set of candidate knowledge-based entities. Again, entity typing can also be used to help entity linking. Here is an example where only 24 supertypes are considered for entity typing. Then the typing will be incorporated into the linking results to remove some irrelevant types. In general, mention detection, entity typing, and entity linking are three related tasks. They have different annotation and loss functions to train, but they can help each other. For example, when typing is more difficult, where there is very few annotation or the number of tabs are large, then adding linking results as features could be helpful. While linking is more difficult, for example, when there are more out-of-sample entities in the test set, adding typing features would be useful. In the literature of general NLP, there are already some existing works doing linking and typing jointly to improve each other. So given the entities, we also want to know what are the relations between each other. And this is what relation extraction does. The task of relation extraction in biomedical domain can have different subtasks. For example, to extract the relations between drugs and disease, drug and genes, or diseases and genes. A more concrete example is shown in the bottom. In this sentence, the entities should be identified with a tab, which is the task of entity typing. And then the relations are determined by the expression of words in the sentence to classify the pairs of the entities into a predefined relation category. Machine learning can be applied here for relation extraction. It is important to know the dependency between the related entities. So a dependency parse tree is widely used in building the initial relations. However, sometimes the best dependency parse tree might not be able to capture all possible relations between words. So a recent work proposed to use several top best trees and get as many relations as possible first, and then used a graph neural network to automatically learn which relation could be more useful to determine the final relation between two entities. Another typical relation extraction in biomedical domain is for n-array relations. This is very useful because in biomedical literature, the facts are usually involving more than two arguments. For example, the use of a drug needs the information of the disease, the dosage, and the form of the dosage, and the target group. Only extracting the drug and the disease may only observe partial information. Partial information may be very useful for common sense knowledge, but for biomedical domain, it's obvious that we prefer to have more accurate information. A graph-based LSTM can also be applied here to extract n-array relations. As there's no trigger argument definition for n-array relations, a graph-based representation learning is more appropriate to aggregate all related information to make a decision. A multi-class classifier can be applied here to identify typed entities. And then the relation classifier will make use of the features extracted by the graph LSTM to make final decision whether we extract a set of entities to satisfy a particular relation. There is another type of information extraction called event extraction. Different from entities and relations, event is more complicated than them. And sometimes relations can be used to determine the inner relations between event arguments. Similar to relation extraction, there are many subtasks for events. According to BioNLP in 2013, there are several domain-dependent tasks. They all share similar annotation schemes. For example, they need to annotate the span of the entity or the event trigger. Then they need to determine the type of the event and the relations between trigger and entities, and etc. So here is a comparison of the entity, relation, and events. Entity extraction is the simplest. Relation extraction determines the binary or n-array relations among entities. For events, we first need to identify the triggers. Here, effects and growth are triggers. And then we identify the relations between the entities, such as the cancer here and activity growth, or the chemical compound L name, which is the cause of the activity effect. It's also to think about using a two-step approach to extract events. The first step is trigger identification and classification. And the second step is to do argument identification and argument row labeling. So both of the steps can be done with a learning-based approach. For example, in this example, a tree-based LSTM is used to get representations based on the dependence parse tree. Finally, we also want to identify the relations among events. Event relations are usually in the form of temporal relation extraction, narrative schema, or discourse analysis in NLP. A recent work has been proposed to analyze the biological processes with more domain-specific relations, such as cause, enable, prevent, and super. In general, they also need to first identify the triggers and arguments, and then identify the relations between events. So the relations between events can be used to answer questions that are related to biological processes. Basically, they need to parse both reference articles and the questions into the same structure. This is the parse of the article, and this is the parse of the question. And then they match the patterns to find the answer node in the reference knowledge graph extracted from the article. So obviously, the data of such process understanding is still very small. There is much work to do for events and their relations in the future. So, okay, we have introduced how we can extract useful information to construct our knowledge graph. In fact, by knowing that we have many ways to do information extraction, we realize that our knowledge graph can be organized in different forms. Therefore, we also need different representation tools to represent the knowledge graph so that many more machine learning algorithms can be applied. So next, we will firstly briefly introduce the possible representations, and then finally show some typical QA examples as knowledge graph applications. A knowledge graph is quite different from other types of graphs, such as social networks. A knowledge graph is typically a semantic network or an information network with semantic meanings. So therefore, the entity's instance can be categorized, and the type of the concepts are usually organized as a hierarchical trees. Therefore, when representing the knowledge graphs, we need to consider the structural and typed information. We can use a multi-relational graph to represent the knowledge graph. A multi-relational graph usually distinguishes the relations between edges. Therefore, modeling with such graph requires special treatment of the typed relations. For example, a typical multi-relational embedding method trans-D treats the triplets in the knowledge graph as translational functions, where the head entity embedding plus the relation embedding needs to be similar to the tail entity embedding. In this way, different types of relations can have different representations to connect entities. This is currently one of the most popular way of doing knowledge graph embedding. The loss is then to maximize the difference between a valid triplet in the knowledge graph and the sampled one. There have been many extensions to this method, mostly modifying the scoring function. For example, the recent model rotate can characterize all 4 properties, including symmetry, antisymmetry, inversion, and composition relations. Another representation is to treat a knowledge graph as a heterogeneous information network. Different from multi-relational graphs, a heterogeneous information network also treats entities differently with different types. When only considering node embedding, heterogeneous information networks may not have much advantage compared to a multi-relational graph. However, when considering higher order relations, it's much useful. Here I show a metapath semantically meaningful to compute the similarity between disease and symptom. The similarity is breached by patient. So all similarities can be simply computed by matrix multiplication. We have a disease patient matrix, and we have a patient symptom matrix. And then the disease symptom matrix can be simply done by the multiplication of the two matrices. So similar to this disease patient's metapath, so similar to this disease patient symptom metapath, we can also define many metapaths or metagraphs over the original heterogeneous information network. So given a metapath, it's also natural to extend the existing homogeneous graph embedding method. A typical method is based on random walk. Here is a random walk guided by the metapath, which is semantically meaningful. Then the embedding that can be learned by standard skip-gram algorithm will eventually reflect such kind of human knowledge. Another representation of a knowledge graph is called attributed network. In fact, we can obtain a lot of attributes from existing knowledge bases, such as Wikipedia, where the info box show a lot of attributes values. Moreover, recently, it's becoming interesting to use information extraction to extract some attributes from the text. So given the attributes, we naturally need to use a different learning algorithm to get the node embeddings. It's already found that we can separate the attribute relations from other types of relations in knowledge graph embeddings. Then the attributes can be incorporated into the node embedding in another signal channel. In this way, the node representation can reflect two types of information. The first one is the attribute value, where nodes have similar attributes should be similar. The second one is the topological structure of the graph, where nodes with similar neighborhood should be similar. It seems that although some researchers have already pointed out that it is very important for this kind of representation, it's still under consideration for the biomedical or healthcare community. As we mentioned, a knowledge graph can also be a tree, especially the hierarchical definitions of the medical or biological concepts. Therefore, it's also natural to consider tree-based representation learning method. In general, we can develop different types of embeddings based on different geometrical observations, including Gaussian embedding, box embedding, and hyperbolic embedding. For example, in hyperbolic embedding, the hyperbolic space is naturally reflecting the tree structure. The Poincare model defined over the projection of the hyperbolic space can, this is a projection, show very natural tree-based relations. In fact, in the Poincare bowl, the distance between 2 points that are near to the central are actually small, while the distance between 2 points that are near to the boundary of the Poincare bowl is very large. So this is very different from the perception of the visualization of the Poincare bowl. Anyway, the representation of the tree node learned by the hyperbolic space is quite efficient. Usually, it needs less dimensions to represent nodes of similar quality compared to other embedding methods. Finally, I would like to mention some applications of the knowledge graphs that can be solved by recent developed graph-based learning methods. The first one is a knowledge graph question answering problem from this nice work at NeurIPS 2019. A typical question is, what drugs are likely to target proteins involved with both diseases X and Y? Instead of using traditional semantic parsing or mapping solutions, a natural way to consider is to use a neural network method. This neural-based method can directly model the questions as a set of semantic operations. In this example, two target proteins needs an interaction operation in the database query. Then they apply such kind of QA problem to a reasonably large knowledge graph containing drugs, diseases, proteins, side effects, and processes. So in general, the intersection operations can be done in the continuous geometric space instead of a symbolic inference. In this example, firstly, they identify two diseases, and then they attend two proteins, and then they need to perform an intersection operation over these two proteins, and then to compare with the result. So then it becomes a similarity measure problem between the intersection results and the target answer. After representing the QA in such a way, we can actually design a corresponding loss and learn it from huge amount of data. Results show that such kind of subgraph matching can solve several kinds of semantic subgraph searching problem. Another prediction problem is that rather than answering the what problem, we can also answer how many questions using neural models. For example, we want to know how many drugs are likely to target proteins involved with two diseases in the knowledge graph. In this way, we need to represent the knowledge graph as a heterogeneous information network and count the subgraph isomorphism in the knowledge graph. In particular, we can borrow the idea from NLP to treat such a problem as a QA problem, where we represent both query graphs and data graphs in the geometric space. Then the counting problem can be predicted by using final representation after interaction between the query and the target representations. Specifically, we can borrow the idea of memory networks to iteratively memorize the interaction between the query and the target graph. So if you would like to know more about the details of this work, please attend to our work at this KDD. So to conclude, in this part of the tutorial, we covered the topic of knowledge graph construction and inference in the healthcare domain. It is a very promising and fastly developing domain. Many recent works have been published. There are also many possible directions using knowledge graphs, such as personalized dialogue systems or recommender systems. With that, I can take questions. Thank you.